Let's look at problem 1498, number of subsequences that satisfy the given sum condition. So here we are going to write a solution using the two-pointer sliding window method. So this problem is similar as problem number 1 to sum. Actually, along this same line of idea, we have practiced a number of problems. So for this problem, first we'll go over the statement of the problem and then work out an examples to fix the idea. And finally, we will write the code by two-pointer sliding window method. And then we want to make several remarks. So first, let's look at the statement of the problem. We are given an array of integers called numbers and an integer called target. So we are required to return the number of non-empty subsequences of nums such that the sum of the minimum and maximum element on it is less or equal to target. So since the answer may be large, so we are required to return the result, the count modulo some big number. So before we look at the example, let's look at the constraint. So constraint 1 says that the num is not empty, and also it has length up to 10 to the power 5th, and the latter means, so if we come up with a solution that has n square term complexity, for example, some test cases may not pass. And the second and the third constraint is about the range of elements in nums and the range of target. So with that said, let's look at the example. So in order to better look at the example, let's emphasize the method again. So the method is two-pointer sliding window. And the condition is that we need to check the min plus max is less or equal than target. And the return is the count modulo some big number. So that's the problem idea. So in order to actually carry out a two-pointer sliding window, we need to sort this sequence. So that actually helps to check the condition more effectively. So basically we are doing a sort. So with that said, let's look at the example 1. So let's copy it here. So yeah, we can start from the very left, which is 0. And in this case, we have 3. So we want notice that this nums is already in sorted order, right? So in general, it may not the case. So when L equals 1, so 3 actually, if we consider this, the set is the minimum and the maximum. And then we consider this one, the maximum is 5, and the minimum is 3. So together it's 8, it's still good. And 6, and the minimum is 3, and the maximum is 6, and we are still good. We cannot go further right. So yeah, so this one, so again, the main idea here is that for each index, or you can understand it as the left pointer, we want to find the count of subsequences starting from in the L and satisfy the condition. Right, so for this one, if all the subsequences starting from 3 and satisfying the condition is sequence of this form, 3, star, and star, right? So 3 is the minimum, and the maximum can be at most 6. So in this case, we can easily count the valid subsequences satisfy the problem requirement. So the last two positions is a binary position. With either we can include that element or we do not include that element. So the count is 2 to the power 2. the latter two is the number of binary positions. So this gives us 4. So now if we look at L equals 1, actually, so we are starting from 5. So this is the minimum for any subsequence starting from 5. But the maximum is always greater or equal than 5. So in this case, we cannot go further. The main reason is 5 is greater than 9 over 2. Actually, this special case concerns about the single element subsequence. For example, we consider this 5 as a subsequence. So then its minimum and maximum are both 5, and 5 plus 5 is greater than 9. So we cannot continue any further. So after now, actually, we can stop, because if we consider L equals 2 or 3, because the number is sorted, so the minimum and maximum increases, or more precisely, not decreasing. So it cannot satisfy the condition. So overall, the problem will return 4. So in other words, all the valid subsequences starting from index 0. So that's the working example. So hopefully it helps fix the idea. So we will write the code, and we will also check several more examples to get a better understanding or feeling. So as it's routine for the two pointer sliding window, we can do step 1 here for the sort. So we can sort these numbers in place. So next we set up the sliding window. So before that, so actually we can do something first for preparation. So L R equals 0 and length nums minus 1. So L is the left pointer and R is the right pointer. So we can initialize the total count to be 0, and there are a big number, so we can modulate that later. So we call it 10 to the power 9 plus 7. So now let's look at the while loop. While L is less or equal than R. So here we are using less or equal because there are possibilities of single element subsequences. And also we need to check the condition, that is nums L is less or equal than target over 2. So if this condition is validated, is not valid, so we have no valid subsequences starting from the position L. So with that said, we want to determine the correct right pointer. So in order to update this, so we can do it in a routine fashion, but sometimes I found that the solution may not pass several cases. In other words, time limited. So we will use binary search here to accelerate a little bit. So we will do from bisect import bisect right. So the update for the right target is like this. R is the bisect right. So the places where we search is nums, and the target is going to be target minus nums L. So that's the target minus nums L is a critical value for this. And the range we are going to start is L and R plus 1. So due to the definition of this bisect right, if you're not familiar with this bisect right, you can either write the binary search yourself, or you can check this module here. So let's come back to the problem. So here, right to this index R, all the numbers in nums will be strictly greater than this critical value. So we want to look at the left. So for this, because this is the insertion index, we want to check this one. by -1. So then we will check if R is the relation between R and L. If R is less than L, so that is, and there's no valid subsequence, we just break. So otherwise, we update. So the total count is updated by this number, 2 to the power the free position in this one. So because the sequence is starting from L and ending at R, so the length is R minus L plus 1, but the left boundary is fixed, so we are going to decrement by 1. So in other words, that is R minus L. So with that said, so we update the right pointer, and also we update the final result, and then we are going to move the left counter to the right. So with that said, we are in a good position to do the return. Step 3, I will return the result. So we're going to return this total count. So modulo this last number, m. Let's see. Let's check for several special cases. Total counts. So here, let's correct that. So it passes the first one. Let's cook some more examples for special cases. For example, if this is 3 and this 9, then we check we should have 1 because 3 is a valid one. 3 plus 3 is less than 9. So we get 1. And let's do another check. We check 5. 5 plus 5 is 10, which is greater than 9, so we should return 0. So we get 0. That's good. So now let's check the generic case. It passes all the cases. It's going to slow, and sometimes I find it cannot pass. So here, with this done, let's look at several remarks. First is that this condition. So actually, we can write this condition by nums L less or equal than target. But for that case, if the nums L is very large, we checked more cases that are not necessary, right? So here also we invoke the binary search module, so for accelerating a little bit. So sometimes we can also just directly moving pointer in a linear fashion from right to left, but sometimes it will not pass the